Hello, my dear students. This is the lecture 3rd on the course Real Analysis 2nd, MMTC 202. In this lecture, we discuss ring, then we discuss Sigma-Algebra, then Borel sets. And finally, we solve some exercises on this course. Those exercises depending on these lectures, which we already delivered here. So first of all, we define a ring. Let x be not equal to phi and r be a class of subsets of x, then R is said to be a ring if it satisfies the following properties. Satisfy the following properties. First property, if A comma B belongs to R, then their union should be in R. This should imply A union B belongs to R. And the second property, if A comma B belongs to R, then this implies A intersection B belongs. This R should be non-empty class. That's the definition of ring. Next we see that every ring is a semi-ring. That's one can easily verify that. One can easily verify that every ring is the property 1 is trivial because phi is there. Since as this R is non-empty, therefore we can choose any element of R. It has at least one element. So let's choose A belongs to R. Then this implies by property second, whenever A and B is in R, then their difference. So it's a difference. Then their difference is again in R. This implies A minus A is in R, then A minus A by property second equal to phi belongs to R by second property. So this proves the first property of semi-ring. Now we prove its second property. Second property means we show that it is closed with respect to intersection. So second property, let A comma B belongs to R, then A intersection B is equal to A minus B. You can easily see this. This is A, that's B, A and B, that's the intersection, A intersection B, and this A intersection B is equal to A minus B. How it is? It's this A is that whole minus A minus B. A minus B is this portion. This is A minus B. So A minus B is that portion. Now what's A minus B? A minus that portion, it's equal to intersection B. And now look at this. A is in R, B is in R, therefore this difference is in R because R is a ring. Now A is in R, that difference is in R. So these are two sets, both are in R. Again by property second, difference of two elements of R is again in R. So therefore it is in R. So that proves the second property. Intersection of two members of R is again in R. Now we prove third property. Let A comma B belongs to R, then this implies A minus B is also in R. So therefore A minus B can be written as finite disjoint union of members of S, because it's itself a member of R. Therefore A minus B can be written as a finite disjoint union of members of R. So thus R is assembly. Thus R is a R is assembly. So therefore every gene is assembly. But conversion not true in general. That's an exercise. Is converse true? Is converse true? Exercise. So that proves this everything. Just next we define Sigma-Algebra. Sigma-Algebra. What's Sigma-Algebra? Sigma-Algebra, it's more than algebra. It is an algebra together with one more property, that it's closed with respect to countable union. An algebra, first it's an algebra. And algebra A is said to be a Sigma-Algebra, is said to be a Sigma-Algebra if it is closed under countable union. Closure under countable union means if we choose any countably many members of A, then their union should be in A. So that is lecture 3. That's for any A n belongs to A and greater or equal to 1, then union A and errors from 1 to infinity is again it's closed under countable union. So next we have an exercise. Every algebra is closed under countable intersection. Every algebra is closed under countable intersection. So show that every algebra is closed under countable intersection. Solution. Let A and B any countably many members of algebra. Since algebra is closed under complementation, so therefore A and complement belongs to A for all n greater or equal to 1. This implies now again this is a Sigma-Algebra, so it's closed under countable union. So that means union A and complement and runs from 1 to infinity belongs to A, and this implies, now apply de Morgan's law, it is intersection A and whole complement and runs from 1 to infinity belongs to A. So now again since A is closed under complementation, so the complement of this set also belongs to A, and which is equal to intersection A and n runs from 1 to infinity belongs to A. So thus A is closure under countable intersection. A is closure under countable intersection. So every algebra is closure under countable intersection. It is closure under countable union. Every sigma algebra. Every sigma algebra is closure under countable union and closure under countable intersection. So next we have a theorem which is very simple. The intersection of sigma algebras is again an algebra. So let A alpha belongs to lambda B be a family of sigma algebras on X, then intersection, their intersection is also a sigma algebra, is again a sigma algebra on X. The proof is very simple. Proof is an exercise. Intersection of sigma algebras is again a sigma algebra on X. And we have a more theorem. So let X be not equal to 5 and F be any class of subsets of X, any class of subsets of X, then there exists a smallest sigma algebra containing F, small sigma algebra A, such that F is contained in A. So given any class of subsets of X which is not an algebra or sigma algebra, but we can always find the smallest sigma algebra A such that F is, there exists the smallest sigma algebra A such that F is subset of A, which contains F. So let's prove this theorem because we use this theorem in the next result. So let this cursive C, it's a family of sigma algebras. It's a family S such that S is a sigma algebra on X and contains S. First we check that this class is non-empty. At least one sigma algebra exists which contains F. So clearly power of X is a sigma algebra. It's sigma algebra on X and this F is always subset of power of X, because power of X means set of all subsets of X. F means a set of subsets of X. It may not be all subsets of X. So that means this F is always subset of power of X, and it's a sigma algebra on X. So therefore this is non-empty. Therefore power of X belongs to C. So it contains at least one member. It's non-empty. So that implies this class is not equal to 5. This class has at least one member. Now, by previous theorem, we know that intersection of sigma algebras is again a sigma algebra. This that's the intersection of all members of C. They are all sigma algebras. And intersection of sigma algebra is again a sigma algebra. Is a sigma algebra, and each such sigma algebra contains F by definition. Contains F. Therefore, this intersection also contains F. So that's let's write this as A. A is the intersection of all sigma algebras. It's again a sigma algebra on X, and this F is subset of T. So this is the sigma algebra on X which contains F, and it is the smallest one also. Also, A is the smallest sigma algebra. A is the smallest sigma algebra. A is the smallest such sigma algebra. Such means the sigma algebras containing F. A is the smallest such. Thus, for any class of subsets of X, we can always find the smallest sigma algebra containing that class. This proves this completes the proof of this theorem. Next, we have the important sigma algebra that's called the Borel algebra. Borel algebra. In this, since we know that every class of sets generates the sigma algebra, generates means there exists the smallest sigma algebra contains that class. So, in other words, we can say every class of subsets of X generates the sigma algebra. Now, if in particular, if we take a topological space X comma tau, then tau is a class of subsets of X. So therefore that tau also generates the sigma algebra, and that sigma algebra is called the Borel algebra because that's a particular class of sigma algebra. It's called Borel algebra, and members of that sigma algebra are called Borel sets. So let's define that Borel algebra. If let X comma tau be a topological space, then tau is a class of subsets of X, and the members of tau are called open sets. Open sets. Tau is a topology on X, so its members are called open sets. So, and by previous theorem, every class of sets generates sigma algebra, and let B be the smallest sigma algebra. Smallest sigma algebra containing tau. That is, B is the sigma algebra. B is the sigma algebra generated by tau. And such a sigma algebra is called Borel algebra. Is called Borel algebra. The smallest sigma algebra B, cursive B containing tau, is called the Borel algebra. The members of B are called Borel sets. The members of B are called Borel sets. Since the members of this Borel algebra, they are called Borel sets. Okay. Since tau is subset of B, so that means every member of tau is also a Borel set, because members of B are called Borel sets. So in other words, every open set is a Borel set. Thus, therefore every open set is a Borel set. But converse is not true. So here is an example. It's very simple. So consider a real line R with usual topology. Consider a real line R. Then this closed interval is not an open set. It's not an open set, but we can write this as it's equal to 1 minus 1 by n, 2 plus 1 by n, union n runs from 1 to infinity. So it's the countable union of open intervals, and we know that every open interval is an open set, so that means it is the countable union of open sets. And also we know that every open set is a Borel set, so that means it is the countable union of Borel sets, but the class of Borel sets is Sigma-Algebra. Therefore this is Borel set because it is the countable union of Borel sets. It's a member of P. It belongs to B as each open interval is an open set, belongs to B, and B is a Sigma-Algebra. B is closed with respect to countable union. It's a countable union of members of B. They are members of B, therefore it's a member of B, and it's closed interval. So that means this closed interval is a Borel set, but it's not an open set. So thus every open set is a Borel set, but every Borel set need not be open set. So similarly, you can prove that semi-closed intervals they are Borel sets, and there are some more examples. You can construct that the sets which are Borel sets but not open sets. So now we have some exercises. Let's do this first exercise. Exercise number 1. Let x comma tau be a topological space. Then show that then S is equal to the difference of the intersection of closed and open set. C intersection of both sides. C is closed and O is open. Is S summation? Is it? How we prove this class is S summation? So it's the class of intersection of closed and open sets. And we know that what do we mean by open set? Open set means the member of topology. Closed set means that its complement is a member of tau. Its complement is open. So solution. We can write this as S is equal to its C intersection. I can write this O as O complement whole complement. But again, this C is open, C is closed and O is open. C is closed and O is open. and this can be written as C minus F, where this C is closed and F is equal to O complement is again closed. So this F is actually the set difference of two closed sets. We show that this class of set difference of two closed sets is a semi-array. Is a set. Class of difference of any closed sets. So first property, we have this phi is equal to F minus A, where F is any closed set. F is closed, but the difference of two closed sets is the number of S. So phi belongs to S. Second property, we put closed with respect to finite intersection. So let's choose any two members of S. Let A1 is equal to the member of S. It's the difference of two closed sets, say C1 minus F1, and A2 is also a member of S. It's again the difference of two closed sets. Then A1 intersection A2, it's equal to C1 minus F1 intersection C2 minus F2, that's equal to C1 intersection F1 complement intersection C2 intersection F2 complement. C1 minus F1 is C1 intersection F1 complement. C2 minus F2 is C2 intersection F2 complement. And that's equal to C1 intersection C2 intersection F1 complement intersection F2 complement. It's equal to C1 intersection C2 intersection F1 union F2 whole complement. That's by De Morgan's law. And that's equal to C1 intersection C2 minus F1 union F2. So it's a difference of two closed sets, because C1 intersection C2 is closed set, F1 union F2 is closed, because all these sets are closed sets. So difference of two closed sets, it belongs to S. So that's S is closed with respect to finite intersection. Next we prove that the difference of any two members of S can be written as finite disjoint union of members of S. So let's choose any two members of S. Let A1, which is equal to C1 minus F1, and A2, which is equal to C2 minus F2. Then A1 minus A2, this is equal to C1 minus F1 minus C2 minus F2. And that's equal to C1 intersection F1 complement difference C2 intersection F2 complement. And that's equal to C1 intersection F1 complement, its intersection with the complement of this set, C2 intersection F2 complement whole complement. And that's equal to C1 intersection F1 complement. Now apply here De Morgan's law, intersection, this is C2 complement union F2. It's here F2 complement. That's equal to, now apply the distributive law of union over intersection. Okay, so this is F2 intersection. F2 intersection C1 intersection F1 complement. Then union C2 intersection C2 complement intersection C1 intersection F1 complement. C1 intersection F1 complement. This can be written as let's write it as C1 intersection F2 intersection F1 complement union, this is here C1 intersection F1 complement intersection C2 complement. And that's equal to C1 intersection F2 minus F1, okay, union, and here we can write it as F1 union F2 whole complement. Therefore this can be written as C1 minus F1 union F2 whole complement. Now look at this union. This is the difference of two closed sets, because C1 is closed, F2 is closed, intersection is closed, minus closed. So it's a member of S. C1 is closed, F1 is, it's not here, complement. C1 is closed, F1 is closed, F2 is closed. So again it's the difference of two closed sets. This is the difference of two closed sets. That's also the difference of two closed sets. So therefore it is a union of members of S. So thus A2, A1 minus A2 is a disjoint, is a finite disjoint union of members of S. Why they are disjoint? Because here we have C1 minus F2, but here we have F2, members of F2 here in this set. So they are disjoint. It's a finite disjoint union of members of S. Thus S is a semi. Thus S is a semi. Thus S is a semi.